Good evening, and thank you for joining us for this live streamed astronomy presentation, The Life and Death of the Sun, presented by Dan Reisenfeld. I'm Rick Wallace with Pajarito Environmental Education Center, or PEEC, and located in Los Alamos, New Mexico, and I will be your host for the evening. We're able to offer programming at this time because of our wonderful members and donors, so we'd like to thank you for your continuing support. So, Dan, let me introduce you. Dan Reisenfeld has a PhD in astronomy from Harvard University. He was in Los Alamos starting in 1998 for 6 years, then moved to the University of Montana for 14 years to teach astronomy, then back to Los Alamos just 3 years ago, and is currently the deputy instrument lead for the IMAP mission, which is looking to map the interstellar boundary, the boundary between our solar system's sun's influence in interstellar space. So, Dan, tell us all about the life and death of the sun.
All right. Thanks for the introduction there, Rick. And hello and good evening, everyone. So I wanted to emphasize that I am very enthusiastic about participation. So if you do have questions that you type into the chat, if Rick can relay them to me, as when I'm taking a breath or something like that, I'm happy to answer questions as we go along. So feel free to pipe up virtually, that is, as we go on. So all right. So then to proceed here. So this evening, I'm going to tell you about the life and death of the sun, which is our nearest star. Can't miss it. It's out there most of the time. So before I get into it, I always get asked questions like this. So why do we study the sun, or why do we study anything in astronomy? But tonight we'll be talking about the sun. Well, first of all, the reason I am interested in the sun is because it's absolutely fascinating. It's just, it is the only star that we can see in high resolution. And so much of what we know about all stars is based on our understanding of the sun. It's, of course, the energy source of all life on Earth. And so wouldn't you like to know as much as you can about something your life depends on? I would. More recently, we've become interested in the sun because of its variability. The solar output changes over time, not by a whole lot, but it does a bit, and that can affect climate. And so we know that the Earth is warming up due to greenhouse gases, but the sun also affects climate. And so we wonder how much of that climate change is contributed by solar variability compared to other man-made effects. It's not that we're claiming that it's all due to solar variability, but we need to understand how the balance between solar variability and greenhouse gases and such interact. And finally, very recently, within the last 3 or 4 decades, solar magnetic storms can affect our technological civilization. There can be storms which cause damage to satellites and can affect the power grid on the Earth and cause blackouts. And so understanding variability and predicting large events is an area of great importance these days. Okay, so that's kind of my pitch to Congress if I were to be giving a reason to get funding for this. So, but let's go and start at the beginning. I'm going to take us through basically the entire life cycle of the sun, pausing for a big bit in the middle on its current states and its interactions with the Earth. But let's start with the beginning. The sun and most stars, well, all stars are formed in what we call nebula, such as the one you see here, which is actually in the constellation Orion. This is the Orion Nebula, in fact. Here, let me get my little pointer set up here. All right, so right in here, this is the core of the Orion Nebula. These are newborn stars right here. In fact, throughout here, many of the stars you see in this picture are fairly newborn. They come out of these gases, which were in many which was primordial gas from early in the life of the universe, and it's the gravitational attraction between gas molecules that builds up clumps of material that leads to star formation. So to the birth of the sun itself, the sun was formed in a disk of gas like this. So this disk is rotating. And whenever you have anything in astronomy where it's rotating, you usually end up with a disk for reasons having to do with the conservation of angular momentum. Anyway, this disk is rotating and it's falling in on itself. And you can see here in this illustration that the core of the disk is getting brighter because as material falls in, it heats up, and as it heats up, it starts to glow. And we can actually see what we call protoplanetary disks or pre-stellar disks in different places. These are all from the Hubble Space Telescope. You can see a little disk here, a disk there, a little disk here, a little disk there. These are all new forming stars and planet solar systems. So now, before I go on, I'm going to use this diagram to track the life of the sun. We can think of this like a lifeline on your, you talk about it on the palm of your hand, but this is a real lifeline in the sense that it charts out the life of the sun as a function of temperature on the horizontal axis, where cool is on the right and hot is on the left, and luminosity, or dim to bright. So stars tend to vary in temperature and in brightness over their life in a kind of well-ordered way. So right now, we are on this phase of the sun's life, where it starts out, because the disk that it comes out of is so large in size, the sun actually, or the gas that the sun is forming out of is quite bright. But then as this disk collapses, it heats up, so the line is moving to the left, but because it's getting smaller, it's also getting less bright for a while. Not so much because the core is getting dimmer, but because there's just less disk glowing, so as the disk gets smaller, it gets dimmer. So here's that disk, and also, by the way, within that disk are little rocky objects that are called planetesimals, which can accrete, and the planets, the Earth and such, are formed out of these as they clump together through gravitational attraction. And here is say a proto-Earth here, and and you can see the sun glowing off to the left over there. So now, for some time, gravitational collapse is enough to power the brightness of the sun, the luminosity of the sun. But eventually, the disk kind of stops collapsing because you get to something called hydrostatic equilibrium, where the infalling of a material is balanced by the outward pressure. And if infall of material was the only source of power for the sun, it wouldn't last very long. And what happens is, in the core of this disk, something exciting happens called nuclear ignition. So the sun today is powered by nuclear fusion. And this diagram takes you through what's going on at the microscopic level inside the sun. The sun is made of, we'll get to this, but the sun's made of mostly hydrogen. And so it's not hard for two hydrogen atoms to find each other. And when they do, and under the intense pressures that are in the core of this proto-sun, these two hydrogen atoms can collide and get close enough to each other that they stick, forming something called deuterium. This deuterium can find another hydrogen atom, and if they collide with enough energy, the three of them will stick together, and you get something called helium-3. And it's helium because there are 2 protons in it, so any nucleus with 2 protons is called helium, regardless of the number of neutrons, which are the green things. And then eventually you build up enough helium-3 that 2 helium-3s can find each other, and they collide, and they form helium-4, which is the normal kind of helium that we blow up balloons with. And it kicks out 2 hydrogens, and those hydrogens are free now to restart the process. So basically, the sun in its core is converting hydrogen into helium and giving off lots of energy, which is what powers it and is responsible for the light we see. All right. So back to our lifeline. So we're now in this phase here. So we get to the bottom of this initial curve, which was due to gravitational collapse, and then hydrogen burning turns on at this point. And so for a few tens or 100 million years or so, the sun moves in this track, and it doesn't get much brighter. In fact, it's even still shrinking in size, so it's getting a little bit dimmer over time, but it's getting a lot hotter as that hydrogen burning kicks in. And finally, we reach adulthood at this inflection point here, where point A. And in fact, you notice there's this line back here, and along this line, any star pretty much will spend most of its life somewhere along this line. The only difference is what its initial mass is. So heavier mass stars will end up here, lighter mass stars will end up here. This line here is called the main sequence. And so here is the sun landing on the main sequence. And this is probably a couple 100 million years after its initial formation. So here we are at adulthood today. So let's look at some of the properties of today's sun. This is what it looks like with a nice filter so that you're not blinded. You can see sunspots. They're often present on the disk of the sun. So if you look through, say, eclipse glasses or something like that, you would see something like this. So now our sun has enough fuel to burn as it is for about 10 billion years. Today, it's about 4.65 billion years old, or about 5 billion in round numbers. And it's pretty much a common star, which is a good thing. We don't want to live in a wild, crazy kind of part of the galaxy. It's a common middle-aged star, just kind of sits there and does its thing for the most part. And as I said, it's pretty much run-of-the-mill. Here's a comparison of different star sizes. Here's our sun with a 1 solar mass, not surprising by definition. There are stars that are smaller, or we call them red dwarfs. The lowest ones have about 8% the mass of the sun. Any lower than that, they're not bright and they're not massive enough to ignite hydrogen burning in their cores. They never get hot enough. But you can see that some stars are much, much larger than the sun. Red giants are very old stars, and blue supergiants are very large, really massive stars, up to 150 solar masses, and they're giant in size. Now, it might be small compared to some stars, but it's huge compared to the Earth. You could fit 100 Earths across the sun. But compared to the Earth, the sun is ginormous. That's a technical term. All right, so some more fun facts about the sun. It contains 99.8% of the total mass of the solar system. Most of that 0.2% is in Jupiter, by the way. It's about 75% hydrogen by mass and 24.9% helium. And that last 0.1% contains all of the other elements in the periodic table up to uranium. Those are basically elements that are either stable or have a radioactivity that is low enough that they can last for billions of years before they decay away. So this is all basically every element, naturally occurring element that we see on Earth also is in the sun. Some interesting things about the extremes of the sun. The core temperature of the sun is 15 million degrees, which is what you need in order to convert hydrogen into helium. And you also need a lot of pressure for this to happen. And that pressure is about 250 billion atmospheres. So that's a really big number. And the density at the core of the sun is about 150 times that of water. Okay. All right. So we actually aren't at point A. We're really at point B in the life cycle of the sun. So basically between A and C is where the sun spends most of those 10 billion years. And we're about halfway through that. And basically, notice what's happening is the sun ages, it slowly is getting brighter. So the sun has brightened in the last 5 billion years between point A and point B to a certain extent. All right, so we're going to press pause on the life cycle of the sun and dwell on what the sun is doing today and how it interacts with the Earth. So as I mentioned, there are these sunspots, and that's kind of where things get interesting in solar physics today. If we look at how the number of sunspots varies over time, we see that there's this cycle, and you may have heard of this, called the sunspot cycle. And it has a period of about 11 years. And so here's the last, 50 years or so, or 60 years now, I guess, of the cycle. So this is the number of sunspots on the sun per month over time. And you see it has this nice periodic variability. We call certain parts of this period, it has special names. When the sunspot number gets down to the smallest, we call that solar minimum with the fewest sunspots. And when the sunspot number peaks, we call that solar maximum. And so this isn't just kind of an interesting curiosity, because associated with the solar cycle are a lot of other aspects that cause variability in the sun. So also, when we look at the sun, this is the visible light picture of the sun. But if we were to take an X-ray telescope and look at the sun, this is what it would look like. I'm sorry, this isn't an X-ray telescope. This is an infrared telescope. The sun can look very different depending at what wavelength of the electromagnetic spectrum we use to look at it with. So our eyes see this, but in different wavelengths, you can see very different things. So in fact, this is the most technical graph I have in the talk today. This is the spectrum of light from the sun. So on this horizontal axis, we have wavelengths of light, and on the vertical axis, we have the intensity or irradiance at that wavelength. And so the intensity of light from the sun peaks in the visible right here. This is the only part of the solar spectrum that our eyes can see. It's a very narrow part, but you can see it's a very important part. It's where the solar spectrum peaks. And in fact, that's not a coincidence. We believe that our eyes evolved to be sensitive to the part of the solar spectrum where there was the most light to see with. It would make sense, right? I mean, it would kind of be silly for our eyes to evolve to detect light out here where there's hardly any intensity. Our eyes have evolved to work where most of the light is. So for example, if we were residents of a planet on some other star that was like a redder star, like one of those small stars, our eyes may evolve to peak sensitivity at some other part of the spectrum, which peaks in the red or something like that. So anyway, but you can also see though that there are different parts of the solar spectrum that there's lots going on, and we can build telescopes that are sensitive to parts that our eyes can't see. So here's the infrared. If you go further over to the right, this is the radio wave part of the spectrum. It's ultraviolet light, extreme ultraviolet light, super extreme ultraviolet light, and X-rays off to the left. So this is what the sun looks like with a radio telescope. Each of those red dots is actually associated with a sunspot. This is, again, what an infrared image of the sun looks like. And we'll pause in the visible. We're just kind of going through the spectrum here. And this is what it looks like in the ultraviolet. If our eyes could see in the ultraviolet, this is what it would see, we would see with our eyes. Now, also, the interesting thing about this light is it doesn't get to the surface of the Earth because the clouds and moisture and the oxygen all kind of absorb this UV light. And so in order to see pictures like this, you have to go into space. So we launch satellites into space with telescopes to observe the sun at different wavelengths. And here is an X-ray picture of the sun. All right, so now back to sunspots. They are just the visible, meaning in the visible part of the spectrum, manifestation of solar activity. But when we look at the sun at different wavelengths, with every set of sunspots, something like this is associated. So this is, again, an ultraviolet image of the sun. And so there's actually a sunspot down in here and another sunspot down in here. And you're actually seeing plasma, ionized gas, trapped in magnetic fields that go from one sunspot to another sunspot. So sunspots are actually regions of intense magnetic field that erupt from the solar surface and rejoin elsewhere. Sunspots often appear in pairs like that. Here's another picture of in the ultraviolet showing what we call this an arcade, sort of a whole bunch along a line of magnetic field lines come out of the sun on one side and go back down on the other. You can see sort of an arcade-like structure here. You can take a little walk through there. And sometimes these areas around sunspots erupt into these things like this, which is an eruption of a solar prominence, often associated with solar flares. So I now am going to pause the PowerPoint presentation.
Dan, before you do that, we do have a quick question. Yeah. When you were talking about the solar abundances, were the percentages based on particle number or particle mass?
So that 75%, 25%, that was based on mass. In terms of number, the number of if you take all the atoms, 90% of the atoms in the sun are hydrogen, about 9% of the atoms are helium, and then that 1% is the rest of the periodic table. So, okay, let's see if I can do this. Actually, I'm going to stop sharing, pause that, go to the movie, share the movie with sound. All right. 8 minutes and our full screen. All right, so we have an orbit around actually it's not around the Earth. There's a place between the Earth and the sun called the L1 or Lagrange 1 point, where the gravity of the Earth and the gravity of the sun kind of cancel each other out. So if you put a satellite there, it'll sit there, and that's a great place to put solar observatories. So we have an observatory at that location called the Solar Dynamic Observatory, and it has these amazing telescopes that are constantly monitoring the sun. And the movie I'm about to show you is made from imagery from what we call SDO for the Solar Dynamic Observatory. So here goes. All right. So let me go back to sharing the presentation here. Okay, so just a couple of comments about that. So as you can see, the sun is incredibly dynamic, and the amount of activity that you see like that varies with the number of sunspots. So the more sunspots, the more solar activity, and the less sunspots, less activity. In that movie, that was obviously time lapse, or maybe wasn't obvious to you, but every frame of that, so it was such that about 1 second of playtime was equivalent to about 30 minutes of real time. So it was quite sped up there, but still enough. It still things change very quickly on the sun. One other comment I wanted to make, you might have noticed a black dot circle going across the disk of the sun a few times. That was actually Venus transiting the sun. SDO captured the Venus transit that happened, I think that was in 2015 actually. So that was pretty fun to see. So
Dan?
All right.
We have another question. How do sunspots form?
That's a long story. But the short answer is, or a shorter answer is, so the sun rotates on its own axis roughly once every 25 days. But it rotates differentially because it's a gas ball. The equator of the sun actually rotates faster than the poles. So the equator goes around once every 25 days, whereas the poles rotate around once every 28 days or so. And so you get this kind of winding up that occurs. So underneath the surface of the sun is plasma, which means that it's ionized gas. So electrons and ions are free to move about. And anybody who's taken any physics will know that when you have moving charges, charged particles, they create magnetic fields. And so that's how electromagnets work. When you send electricity through a wire, it creates a magnetic field. And so these moving charged particles create magnetic fields, which in turn get wrapped like rubber bands around and around as the sun differentially rotates. And as the magnetic fields get stretched and pulled on like taffy, they eventually build up enough magnetic energy that they erupt from the surface of the sun. And when that magnetic energy eruption occurs, you see a sunspot. And that's about as far in depth I can go. I could give a whole talk on just sunspots if you let me. So I'll stop for that. So, okay. And anything else, or shall I go on?
Thanks, that's great. No, nothing else so far.
Okay. All right. So, go to a movie. So we've been talking about solar activity, but it isn't always as active as it is today, the sun. It turned out that during the late 1600s, early 1700s, there was a period in Europe known as the Little Ice Age. And it might be a coincidence, we don't really know, but it corresponded with a really odd period in sunspot observations. So we've literally been observing sunspots since Galileo first peered at the sun in, I think, 1605, when he first put his telescope and looked at the sun. He discovered sunspots. And so ever since then, we have basically been charting the number of sunspots over time. It's a pretty easy thing to do. You don't really have to have a very good telescope. And so they've been looking at sunspot numbers over time. And so they had already observed a sunspot cycle, but then it disappeared and was gone for something like 60, 70 years. And this kind of corresponded to when the little ice age occurred in Europe. And then it came back, it kicked back in, and it's been doing fine for the most part ever since. This black line here is kind of the average over time. And so this disappearance may have been associated with the little ice age. During this period of time, glaciers grew throughout Europe. The New York Harbor froze. The Thames froze often, as shown in this picture below. Famines were common because the growing seasons were shortened. And one can wonder if this was due to the absence of solar activity. Now, you can also see from this chart, especially if you look at the black line, the average number of sunspots has been kind of slowly gaining speed over the years. And so this is one of the reasons why scientists think that solar activity might have something to do with climate change and global warming. Yes, steady rise in activity. Now, however, recently, the last few solar cycles have been getting smaller and smaller. We don't know if we're headed to another little ice age or not, but we have noticed that this you notice is 2020 here, so this is last year. The number of sunspots has been declining since the peak in 1990 pretty steadily. And we've experienced some of the deepest solar minimums. So notice that this minimum is lower than that minimum, and this minimum was lower than the one before it. And so something obviously is changing on the sun. We're seeing the lowest level of activity in 2 centuries right now. And so how that is related to climate is still not clear. So, all right, now I mentioned, I should say, that there's other ways in which solar activity affects us, and that has to do with solar storms. Now, we have a special name in astronomy for these things. We call them coronal mass ejections. So I want to show you, so this is what the sun's corona looks like, which is the part of the sun that we can only see if we blot it out during an eclipse with a moon well placed here. Here's the moon blotting out the sun in 1980. In India and here in the Philippines in 1988. This image was taken during solar maximum. This image was taken during solar minimum. So lots of sunspots, not as many sunspots. And you notice the structure of the corona is quite different between solar maximum and solar minimum. In fact, there's these dark openings near the poles that we call coronal holes, in fact. Often during solar maximum, we also have lots of coronal mass ejections. So this is a time sequence of 6 images of the sun. And this was taken from space with the SOHO Solar Heliospheric Observatory. And they had a coronagraph, which could make an artificial eclipse whenever they wanted. And so it blots out the disk of the sun, and you can see here a coronal mass ejection coming off of the sun. These things are huge, and if one is directed towards the Earth, they can be quite have a large impact on the geomagnetic activity around the Earth. As I said, they're quite huge. Just to put the comparison, remember, the Earth is tiny compared to the sun. So this is the Earth. Here's a coronal mass ejection. Watch out. So anyway, when one of these things comes towards the Earth, all kinds of things can happen. Here's a coronal mass ejection in this illustration coming towards the Earth's magnetic field, which is depicted here by these light blue lines. And in fact, luckily for us, the Earth's magnetic field acts as a barrier, so we don't get a direct hit by these coronal mass ejections. They tend to kind of go off to the sides. But notice how the Earth's magnetic field has these holes here at the poles. And because of that, particles from coronal mass ejections can enter the Earth's what we call magnetosphere and actually make it all the way down to the lower atmosphere where we see this, the aurora. So you've heard of the aurora or northern lights. These are caused, most of these are caused by coronal mass ejections. They certainly, that's when they become the brightest, is during these events. The aurora are around all of the time, but they're not nearly as intense as they are during the coronal mass ejection storms. So these coronal mass ejections and the storms associated with them can cause all kinds of havoc in our modern society. As I mentioned at the beginning, they can cause charging of satellites, which can basically cause them to spark and out and actually get damaged. They can damage solar cells on satellites, shortening the life of satellites. They carry a lot of radiation, so they can affect astronaut safety. They can interfere with communications. And one of the biggest disruptions is actually they can drive currents, electric currents, along either power lines or even in pipelines. Think of a pipeline as a big long wire or power grids going along the surface of the Earth, and you have this changing magnetic field. And again, from physics, we know that changing magnetic fields can induce electric currents in wires. That's how we generate electricity, in fact, in power plants. Anyway, so imagine you have this giant storm generating a current in a pipeline or in a power lines, and you can blow out transformers. You can do all kinds of stuff. So this is a big reason why this whole domain, by the way, is called space weather, and it's one of the major sources of investigation in the last 20 years in our field. All right, that's the end of the portion that we'll talk about solar activity and the Earth and things like that, and we're going to get back to the life cycle of the sun. Pause here for a drink of water. So for the next 5 billion years, the sun is going to move along its lifeline, getting slowly brighter. And that's not necessarily a good thing, because even though the sun is going to, more or less as far as it's concerned, stay about the same, getting slowly brighter means it's getting slowly hotter here on the Earth. And in 5 billion years, over the next 5 billion years, the sun is going to double its energy output, basically. In fact, in about 1 billion years, the Earth will become so hot, it will become uninhabitable. So we need to figure out where to go. And we have 1 billion years to find an answer, to find another home for ourselves. That is a long time, though. So I don't think we have to quite start investing yet, but keep that in mind. All right, so this main sequence burning, this point between A and C as the sun gets slowly hotter, but stays here for about 10 billion years, it's converting hydrogen into helium in its core. Now, there's not an infinite amount of hydrogen, and eventually it'll get to the point around here where the core hydrogen is spent out. Basically, all of the hydrogen in the core, I'm talking about like the inner 10% of the star, has been completely converted into helium. And when that happens, the core of the star is actually going to shrink because there's no longer pressure from the power generation to keep gravity from pulling the star in on itself. And as it shrinks, it heats up again. And it gets even hotter than it did the first time it formed a core. And it'll get so hot that it can start to fuse helium into heavier elements. And that occurs in this kind of wiggly part of the lifeline where there's these periods of what we call helium burning. And so helium is going to get converted into carbon and oxygen and nitrogen during this helium burning phase, where all the helium nuclei get packed together. And again, it's going to give off energy when the fusion occurs, and then energy is going to keep the sun alive for a bit longer. But the hydrogen burning phase goes on for 10 billion years. The helium burning phase is only going to go on for maybe another 100 million years. So this happens fairly quickly. And while this is happening, the sun is going to get huge. So in this picture that you saw before, this red star down here depicts how big the sun is going to be during the helium burning phase. In fact, it's going to get so big that it's going to engulf Mercury and Venus and possibly the Earth, although it might not. But it doesn't matter anyway, we'll be all gone by then because of the heating that occurred sooner. But basically, if we figured out a way to live with a sun that's giving off twice as much energy for the last 5 billion years, it's going to be literally toast after that. So that'll be the end of the inner solar system. So eventually the helium in the core is spent, and the sun goes through another interesting set of gymnastics where the core shrinks in on itself. There's no longer, the core is not large enough. It doesn't have enough material as it shrinks, for the temperature to increase to the point where heavier elements can be fused. And so helium is the last source of fuel for our sun. More massive stars than the sun can keep going by burning helium and carbon, oxygen, nitrogen, and then burning the carbon, oxygen, and nitrogen into heavier elements, but not our sun. So once that helium is spent, the core actually gets hotter because it's shrinking again, but it's also getting dimmer, and eventually it starts to even cool and basically fades away. And down here, it'll get so dim and faint, we call it something known as a white dwarf star. The outer layers of the sun, though, will be shed through some kind of hydrodynamic interaction, which causes the outer layers of the sun to be blown off, and you get something like this, which is called, in astronomy, we call this a planetary nebula. That has nothing to do with planets. That's just the name because at one point they thought this whole thing was a planet. But it's basically a shell of gas that's been expended by a dying star. You can see the star there. That's the white dwarf in the center. And that will be the end. And that's all I have for you tonight. So thank you for your attention, and I'm more than happy to answer any other questions you might have.
Okay, we do have a couple questions. So one question is, will the sun's, and this was asked when the sun was, you were talking about it still on the main sequence, but it's perhaps more relevant later on. Will the sun's gravitational pull vary as it ages?
Well, what varies is the amount of exertion of outward pressure. So the gravitational pull is this kind of steady, relentless inward draw. But as power sources are ignited in the core that generate heat, that heat creates pressure, and that pressure pushes back and maintains this equilibrium between outward pressure and the steady, constant inward pull. And so that the pull is constant, the gravitational pull is constant, but the outward pressure varies a lot over the age of the sun.
And another question is from Lisa. Why aren't more objects in our solar system pulled directly into the sun? Things like comets and asteroids, etc.
Excellent question. And if you recall at the beginning, I talked about angular momentum. Anything that is rotating will have what we call angular momentum. And it's a conserved quantity in physics, meaning that the amount of angular momentum in an ideal situation that an object has cannot be created or destroyed. So imagine you are spinning on ice or something like that. Figure skaters do this all the time, is they pull their arms in and they spin faster. And then if they let their arms back out again, they spin more slowly. So angular momentum is the product of the sort of how far out your arms are and how fast you spin. So as something comes in towards the inner solar system, like a comet, if it's coming in at an angle, so it has angular momentum, as it approaches the sun, the distance from the sun to the comet is getting smaller. That means the comet is going to go faster. So basically, the closer the comet gets to the sun, the faster it's going to move in the arc around the sun. And so rather than crashing into the sun, it avoids it, goes around it, and goes back out again. And that's the same principle as to why the planets don't fall into the sun. They are going in nice circular orbits, but if the Earth were to stop for some reason, it would fall straight into the sun. But because of its angular momentum, it keeps going into a circle, even though it's being pulled constantly towards the sun. And so it's that balance between angular momentum and gravity that keeps objects trapped, but don't allow them to directly fall into the sun. You have to completely lose all of your angular momentum to fall into the sun.
Okay. After the sun dies, does the gas spread away, or does it reform into a star in sort of a repeating life cycle?
So good question, and there's a long story there. So from an individual star like the sun, if it weren't for other gas that was out there, all of this gas here would dissipate and just kind of continue to spread out over time. And but imagine there's another star that also shed its outer layers, either through something like this, a planetary nebula event, or through something we call a supernova, where a star completely explodes, the core goes, everything goes, and all of the elements that were formed during fusion get cast out into the galaxy. So if you have a bunch of these events where you have gas clouds from different dying stars, and those gas clouds collide with one another, then you can form new stars out of the accumulation of gases from multiple other events. In fact, our sun is a second generation star, meaning the first generation of stars were just hydrogen and helium. There were no heavy elements, no uranium, no iron, no nickel. That was all formed from the Big Bang, hydrogen and helium, that is. So only through the manufacturing of elements inside the cores of stars do we even have anything in our own sun other than hydrogen and helium. So some old star blew up, shed all of its iron and nickel and oxygen and nitrogen, and out of that, a new star was formed, the sun, and other stars from that second generation of star formation.
And presumably the rest of the solar system as well, hence Carl
Right.
Sagan's expression, "We are all star stuff."
Indeed, we in fact are made up of material that was made through nuclear fusion and other stars that have long ago died and blown up.
Which brings us to another question about as that material is being blown off the surface of the sun toward the end of its lifetime, does that affect the orbit of the Earth?
That's a good question. This particular material is pretty low in density, even though it's quite bright here. I would doubt, although this is more of a speculation than like an area I've studied. I suspect that the density of this material is too low for it to have affect the orbit of the Earth. Now, when the red giant phase of the sun occurs, before this happens, where the star gets so bloated that it actually extends out to the orbit of Earth, I would not be surprised if there is enough material in the atmosphere of that star to cause drag, which would cause the Earth to spiral into the red giant. But that's sort of an educated speculation on my part.
is there enough material shed in the planetary nebula phase to reduce the gravity of the sun enough that the Earth might spiral away slightly, cooling it a little bit or keeping it from falling into the red giant?
Probably, yeah. I mean, I don't know exactly the amount of material that our sun would dissipate during the planetary nebula phase. I don't think that's well known, but it is a significant fraction of the mass of the star. And by significant, I mean, measurable in, a few percent to tens of percent. But so the Earth wouldn't necessarily escape, but it probably, yeah, that's a good point. It probably would end up in a larger orbit as a result of that.
Russell asks, is there some event that could cause the sun to go supernova rather than become a white dwarf?
Not likely. The only situation where smaller stars like the sun may end up going supernova is in the case of something called well, if they're in a binary system where there's two stars in orbit around each other, and say one of the stars goes through its red giant phase and gets really big, and so it gets so big that the other star, the sun-like star, starts basically sucking material off of the other star, and it falls into the sun-like star. And so over time, the smaller star can actually gain mass. And if it gets to a point where its mass is 2 to 3 times the mass of the sun, yeah, that can actually go supernova. So that is a possibility in binary star systems. But a lone star like the sun, without anything else to come along and give it more mass, its fate is sealed.
That's probably somewhat comforting, I suppose.
Yes.
Okay. Are there any other questions? Let's give it a few seconds and see if anyone happens to be typing anything. Those are all
These are great questions, by the way.
Yeah, those are all the ones we have so far. Okay, it looks like we have no more questions, so I will say thank you again to Dan for giving us this great presentation. Thank you for joining us tonight. And again, thank you to Dan for this great presentation. And hopefully we'll see some of you next week.
Thanks, everyone. Thanks for coming.
Thank you. Good night.